in today's class, we'll be seeing about one of the most important routing algorithm in the form of a distance vector routing. So before going in to see what is exactly or how it is going to function or how it is going to decide what is the route we are going to take it up. So I've just taken up, you can side by the right hand side, you can see that I've taken up a tree-like structure which is connected with various links. So this is what the node structure or a tree structure. We are going to take up an example to study the behavior of your distance vector routing. So before getting into an analysis, let me describe you the basic or let me describe the functionality of these algorithms. One is, it is an iterative, a distributive and asynchronous algorithm. So there is a question will rise that what is meant by iterative. So when you take up an iterative, one of the best part of this distance vector routing algorithm is that unless until it gets all the updation, the process will be keep on continuing. For example, if the node A wants to have a transmission to B or wants to have a transmission to C, it will keep on acquiring what is the statistical information which is available in B, what is the cost available, what is the transmission duration it takes to reach the B. These are the details which will be keep on acquiring. Once if it is acquired, it will start the process. That is what we call it as an iterative. See, when it comes for your second statement, it is distributed. It means that, so I'm just coming back to this network structure which I have drawn here. You can find that node A is directly connected to B and it is directly connected to C. See what it does that it gets the information from B and it also gets information from C and compute the distance between A and B, and it computes the distance between A and C and calculates the other parameters values, and once again it distributes back to the nodes that I have all these sort of information. That is what we referred as a distributed. And the last one, it is an asynchronous. So it means that the node which is connected here or which are connected to a link here doesn't work synchronously with all the nodes. It doesn't mean that when A is working, B should also listen or she should also listen. That is what we call it as an asynchronous. And the other name for a distance vector routing, you can make it up as a dynamic algorithm, or we can say call it as an adaptive routing algorithm. So when it comes for a routing, as we seen in the previous cases or previous class, so each and every node should maintain a routing information table, so which we call it as here as a vector table. It means that A should have a table, B should have a table, C should have a table, and D should have a table, and E should also have a table. So these table is commonly referred as a vector table. So once if the tables are going to be maintained, from the table we are going to calculate, or from the table we will be finding out what is the shortest path or what is the minimum path which required to reach my destination. So to find that shortest path, let me have some sort of a mathematical calculation here. I'm involving the mathematical calculation. For that, let me take up let d of x of y be the least cost path from the node x to the node y, where x is a source node and where y is the destination node. So I have to find what is the least cost. To find the least cost of d of x comma y, I'm going to use a mathematical equation in the form of d of x of y, which is equal to minimum of c of x comma v plus d of v comma y. So as we know that x is a source node, y is a destination node, where minimum is the minimum value I'm going to find out here, where c represents the cost of the present node, or we call it as a source node, where the v represent the intermediate nodes. So I'm repeating once again, where x represent the source node, where y represent the destination node, where C represents the cost of the source node and the intermediate node. This node is nothing but the node which is available in between of your source and destination. That is, for example, if I am going to find out between A, C and D, whereas X will be treated as A, whereas Y will be treated as C, here the V is nothing but the node C. Clear? Now, let us take an example. Let us now analyze what is a, rather than analyzing, let me form a routing information table which provides you the details of all the nodes. From there, we'll use the distance vector algorithm, or we'll use this mathematical equation to find the least cost path. So one more important information you should remember is that, so this mathematical equation, that is d of x of y is equal to minimum value of cost of source node comma intermediate node plus the distance of your destination node. This equation is commonly known as a Bellman-Ford algorithm. Sorry, it's a Bellman-Ford equation. This is what we referred as a distance vector routing, or else we can refer this equation as, or this algorithm as, a Bellman-Ford algorithm. Clear? Now we'll form an example. We'll form a routing table. With the help of these mathematical equation, I will show you how to find the least cost path. Or else there is an alternate method is there. From the diagram directly, we can find the alternate cost. That is what I am going to explain you right now. In the previous slide, we have seen the basic things about a distance vector routing, or we can call it as a Bellman-Ford algorithm. Now, what we are going to see in this section is how we are going to form a table from the network graph which I have given you, or which we have taken as an example. So we have a 5 nodes are there. Let me make up a statement as node, rather than saying let me have a 2 columns. Column number 1 is for a nodes and the column number 2 is for adjacent nodes. I am just splitting the second column into 5 with a node A, B, C, D, E, and I am just noting down A, B, C, D, E. So to fill up this vector table, I am just going to follow a rule, is that whenever there is a direct connection between the nodes, that will be marked as an active connection, or that will be considered as an active connection. When there is no direct connection, it is considered to be the distance is infinity. So with that, I will be marking up a table. And one more condition, if the same nodes are going to come, I will be marking it as a 0. So let me take up an example with node A. So where I am going to have 5 adjacent nodes are going to be there, starting from A, B, C, D, E. So from A to A, I am just making up a distance is 0. From next one is, so from the structure, I am finding that A is directly connected with the 2 nodes. One is with B, another one is with C. So just directly going into the table. So by the graph, I am finding that what is the number which is written in the link between A to B is assumed to be the cost. So since the number written is 2, I am just making it up as 2 here. And for B, sorry, so from A to B it is 2, from A to C it is 4. So since we don't have a direct connection between A to D and A to E, I am making it as infinity. And similar to that, when I am come for a B, I am filling the table as it is 2, B to B 0, B to C 5, B to D there is no direct connection, it is infinity, and B to E there is a direct connection, I am making it up as a 0. Like this we have filled up this the vector table, or we call it as a routing table. The next what we are going to do is that, let me take up any of these 5 nodes as a source node and then find what is the shortest distance using this mathematical formula. So there is a possibility, or there is an alternate way. You can directly from this diagram you can find out what is the alternate way to find the least cost. That I will be teaching you in the next one. Okay, here, as I said you, I have taken an example as source node is A, and I have taken a 2 destination node, because based on the previous table which I have drawn, we have yet to find what is a distance I need to have, or what is a cost I need to have so that I can reach by D and E. Now let me take up the destination node as D. See, from this diagram, I am finding that what are all the possible routes from A I can reach D. So I have just listed out. The route number 1 is where I am going is A, B, E and D. That is the route number 1. When it comes for route number 2, A, C and D. Route number 3, A, C, B, E and D. It's a route number 3. And the fourth route I am taking it as A, B, C and D. So there are, I have taken up 5 routes I have taken up. Now what we are supposed to do is, I am adding the cost involved in these routes. So let me take up route number 1. What is the cost between A to B? It is 2. The next, what is the route is, I am traveling from B to E. So B to E, what is the cost? It is 7. So already we have a cost is 2. 2 plus 7, it is 9. And then what is the other route I am traveling? It is E to D. So E to D cost is 2. So put together 7 plus 2, 9 and we have 11. Now take up a route number 2. It is A to C and C to D. So what is the cost of A to C? It is 4. And what is the cost of A to D? It is 3. So 4 plus 3, it is 7. And now I am just taking it up the third route. A to C, 4. C to B, 5. 4 plus 5, 9. Then B to E, it is 7. So put together I have 16. Now E to D, 2. Put together I am getting as 18. And I am just taking the last route, A, B, C, D. So A to B it is 2, B to C it is 5, C to D it is 3. So put together 5 plus 3 plus 2, it is 10. So now we have a 4 cost is there. From the 4 cost, find out what is the minimum cost it is going to be there. So the minimum cost is route number 2. We call it as value as 7. So make a note of this 7. We'll be seeing update in the table. Clear? Now, so once if I find what is the minimum cost which I'm going to take it up to reach my destination, I have to find what is the next stop so that I can reach my destination. So because the next stop plays a major important role in transmission, because the data which I'm going to transmit from my parent node will be staying in the next stop. So when it comes for this route number 2, we have a ACD. Our next stop is supposed to be C. Clear? Now similarly, we'll find what is the route for E. Now we have taken as a second one as a node E, and from source node A, we have taken what are the possible 4 routes are there. Route number 1 it is ABE, route number 2 is ACDE, route number 3 is ABCDE, and route number 4 is ACBE. Now similarly what we have done for D, I am just going to calculate here. So find the cost involved in the route number 1, ABE, 2 plus 7, it is 9. Then the route number 2, ACDE. So where we have a route cost is 4 plus 3 plus 2, 7 plus 2, 9. And then the third one is ABCDE. A is 2, B is 5, 7 plus 3, 10 plus 3, 12. And the last route is ACBE. We have a 4 plus 3, 7. 4 plus 5, 9. 9 plus 3, it is 12. And now, so since in this case what I am going to find is there are 2 routes are there which is equivalent to the same value. So I am just completely ruling out of this cost. Now question will rise, which is supposed to be the minimum cost. By no doubt I'll be saying it's the cost required to reach my minimum cost required to reach is 9. So now the question will rise whether the next stop is going to be either B or E. This is where the question will rise now. So whether you want to go with either a B or E. So since the entire algorithm is depending on the concept of low cost, or rather than saying a low cost, concept of minimum cost, you can choose any of these as a next node. Either you can, sorry, it's not E, the next node is C. So either you can choose node next stop as a B or next stop as a C. It depends on the network administrator. So now I'll show you the character table of node A structure, where you can find whether that node is entire column has been, entire row has been filled starting from A to E. We have a route for all the nodes, like from A to B or A to C or A to D or A to E. In where I have just given you two tables are there. Whereas this table number 1 is, we'll call it as a complete routing table for the network graph which I have drawn here. This is a next hop table for the various destination node which you have taken from the routing table here. So the complete table has been found out with the help of this mathematical formula or from the direct method, for which involves a minimum cost. And you can find that when it comes for the next stop table, we have a source node and destination node. S node is nothing but I've just mentioned it as a source node. D node is nothing but I've mentioned it as a destination node. Where the cost is nothing but the minimum cost, where a hop is the next node through which I have to travel to reach the destination. So whereas here in the previous table, in the very beginning of the table, we have seen that D and E is infinity, where from B to D it is infinity, and C to E, wherever I marked in orange color, it is we have termed as an infinity here. So with the help of a Bell-Manford equation as well as the direct method, we have found that the cost involved to reach D from A is 7. The cost involved from A to E is 9. And similarly, cost involved from B to D is 8. Cost involved from C to E is 5. And the same replica is there for D and E. Now, so we have to find what is the next node. If I want to reach D, what is the next node where I have to travel? From this table, we will be able to find out only the minimum cost required, or the cost which is involved for direct transmission. Now, what we need to know is that what is a hop next stop, so that I can decide when I'm going to transmit the data. So to do that, I'm just making up a second table which I've drawn here. It's a node A. Sorry, rather than node A, I'll just mention it as a source node, destination node, cost and hop. So where I've taken up a destination node is A, we know that, sorry, source node is A, and we know that the destination node is D, and the cost involved, I'm just taking it up from the table. It is 7. So when it comes from the hop, we have based on the routes which I have taken and the minimum route, I'm finding that the next stop is C. When it comes for E, so the cost involved is 9. The next stop is 9. Next stop is B, where we found that there are two hops is possible. One is either a B and one is C. Based on these two, I'm just assuming that B is the best hop for me to go for a trans, because the cost involved from the initial route from A to B or A to C is A to B is 2, A to C is 4. Put together, I'm getting a 9. Even if I'm going to travel with A, B, E, I'll be getting a 9. Even if I'm going to travel with A, C, D, E, I'll be getting it as 9. Sorry, not A, C, B, D, E. It is A, C, B, E. I'm just getting it as a 9. So what is our ultimate aim is that since we have to have a minimum cost is required, I'm finding that both the cost is going to be 9 only. Now, when I've said in the previous one, you can choose any slide, any nodes which is either it is B or a C. You can have any node as a next stop. But when I'm just going to project it in the table, I'm just making up my mind as to be altered. So the initial cost, which is I'm finding it as minimum, I'm just taking it up as a next stop. So compared to this, 2 is the minimum value, so I'm taking it up as next stop. So I'm just coming back for B. It is D. So destination is D. Cost is 8, and the next node is, or next stop is C. And when it comes for a C, my destination is E. The cost is 5, and the next node is, or next stop is D. So this is what the next stop table is going to be there. So this gives you the complete nature of how we are going to work out, or how we are going to find out what is the shortest distance, or what is the best path to reach your destination on the source node with the help of distance vector routing. In next class, we'll be seeing about a link state routing. Thank you.